Well, it is a pleasure to start this final day of geometry, group actions, and singularities in the Americas with one of our brilliant postdocs at IMSA. He studied his PhD at the CIMBESTAB, Center for Research and Advanced Studies in Mexico City. And he will be speaking, Enrique Becerra, and he will be speaking about the Hodge filtration by H and the spectrum of the Val singularities. Enrique, thank you very much.
Okay, thank you. I would like to thank to the organizers for inviting me to speak here. And well, I'm going to talk about this joint work in progress with Professor Katsarkov and Professor Lupercio. And okay, so the plan of the talk is as follows. I will start by recalling the a notion of grading, which appears in the approach of Ito and Wright about Mackay correspondence, the classical Mackay correspondence. And then I would like to relate this filtration by H, or to to relate this filtration by H, or write it in terms of a Hodge structure on the cohomology of a certain orbifold, which is going to be just the classifying stack of a finite group. And so I will compare some natural filtration which appears in non-commutative Hodge theory and this H filtration. And at the end, I will explain a little bit how we can use these ideas in order to compute the spectrum of the classical Val singularities. Okay, so let me start with the filtration by H of Ito and Ray. Here, this mu n will denote the group of n roots of unity in the circle, in the complex plane, and I will take the procyclic group, the inverse limit of these finite cyclic groups. And let me consider as well a finite group of SLN with of the matrices with the special linear group, complex matrices with in the special linear group, and I will denote the group of homomorphisms from this mu, the group of groups of unity, into G, like this. And the point is that the group G acts on this set of homomorphisms by conjugation on the right. And also, it has an action of the roots of unity by reparametrizations, so to speak. So we can think of this set of homomorphisms. Sorry, we can think about this set of homomorphisms as a certain loop space related to the group G, and so we can take the rotation action with respect to mu, and we obtain in this way a sort of reparametrization action on this loop space. So I will denote by gamma the quotient by the set of homomorphism from mu to G, and this is in correspondence, in one-to-one correspondence. There is a bijection between this quotient and the set of conjugancy classes of G. So note that in this way we obtain an action of mu by reparametrizations of loops on the set of conjugancy classes of G, and this will be important later on. So now, so this is for this can be defined for arbitrary finite group, of course. But in the case when G is a subgroup of SLN, we can define a grading, or we can split this gamma into pieces in terms of the so-called H introduced by Ito and Wright in the context of Mackay correspondence. And the idea is that we can take an arbitrary element of G, and by fixing a base, we can diagonalize this element, and so we can write down this G as a diagonal matrix with in such a way that the diagonal contains just roots of unity. So this R is the order of our element G, and if R is the order of G, then we can choose some numbers A1 up to AN, which are positive and less than R, which is the order of G, and we can obtain an expression like this. So once we have this expression for an element G, we can take we can define the H of G by means of this formula. So we can take the sum of
this is the same formula that is used for L1 and from 24 distribution sectors, so it's kind of
it is
the same.
Yeah. So since G is in SLN, then this means that this sum is divisible by is concurrent to 0 modulo R, and we can define the H in this way. So the point here is that this definition of the H depends on some choices that we need to make, but it is well defined if we pass to this set of conjugancy classes, defined in this way. So we can define the H of an element of this set gamma, and a result of Ito and Ray is that the H decompose gamma as a disjoint union of this gamma sub k, where gamma sub k is consists of the collection of all conjugancy classes which is of HK. So we can decompose gamma, we can split gamma in this disjoint union, and moreover, the action by reparametrizations of loops, the gamma by rotations of this mu on the set of conjugancy classes is compatible with this decomposition. So we have this decomposition, and this is the action by reparametrizations with respect this gradient. Okay. So the importance or the relevance of this notion of H in the classical Mackay correspondence is or has the following geometric intuition behind it, and the point is that if we take the quotient variety, so we have this finite group G which is acting on Cn, and we can take the quotient, and the point is that if we take an arbitrary resolution of singularities of X, then we have the exceptional divisor, and we can define the discrepancy divisor in this way. And there is a one-to-one correspondence between the components of the discrepancy divisor, which of certain fixed discrepancy with the elements of H, the discrepancy plus 1. So we have a one-to-one correspondence, which is in which the discrepancy is related with the H in this manner. Okay. So, for instance, or in particular, this means that there is a one-to-one correspondence between classes of H1, which are so-called junior elements of the grading, and the discrepancy decrepant divisors, decrepant divisors in the discrepancy divisor, which are those components of discrepancy 0. Okay. So now let me show a couple of simple examples of this grading, and so let me consider the finite subgroups in the case of SL2C, which is the case of the classical Mackay correspondence, and there is a classification, a well-known classical result of Klein, let's say, which says that all finite subgroup of SL2C are given by the cyclic groups and the dihedral groups of any order, and also 3 exceptional finite subgroups which are related with the symmetric groups of the platonic solids in the 3-dimensional space. So, for example, suppose that we consider this cyclic group of 5 elements, and these correspond to the rotations of a pentagon, of a regular pentagon in the plane. And in this case, we have an abelian group, and the conjugancy classes are then in correspondence with the elements of the group. So in this case, the action by reparametrization is just the action by cyclic permutations of the classes. So this numbers here correspond to the conjugacy classes of this set mod 5, and the action of mu, which is given by reparametrization of loops, just rotates these 5 elements. So I put here the numbers corresponding with the corresponding rotations given by this action, and this will be important, and moreover, it is related with the spectrum of the corresponding singularity A5, as we will see at the end. So on the other hand, if we consider now the dihedral group, which is the group of symmetries of a square, we have this dihedral group is the semi-derivative product of set 4 and set 2, and we have here 5 conjugancy classes. So the center of this group has 2 elements, which are, in this presentation, the center corresponds with this with the first 2 elements here. And so we have a conjugancy class for the identity element, a conjugancy class for the other element, the non-zero element in the center, and we also have 3 conjugancy classes, each one of size 2, with 2 elements. And the action by reparametrizations of loops, in this case, decompose or splits this set of conjugancy classes in 2 parts. So the first part is just a cyclic permutation of between the first 2 elements. So we have a set 2 action with this part with the first 2 elements, and we also have a cyclic permutation of the 3 last conjugancy classes. So we decompose this action of mu on gamma in 2 parts. The first one corresponds with these 2 with this reflection, well, with this rotation corresponding to set 2, and we also have the corresponding rotations of the last 3 elements. So we obtain a collection of numbers like this. Okay. So now,
excuse me.
Yeah.
Could you go to the previous slide?
Yeah.
I mean, could you explain a little more why it's 1/3? And I mean, so I ask you why it's 1/3 and 2/3?
Yes. So we have this gamma, which is split in 2 parts. So we have the first part correspond with the elements in the center, which is e and x squared, and this can be we can add to this another set now of 3 elements, which is x, y, and x times y. And the point is that we have an action of mu2, which is just set by 2 here, which is just the action which flips these 2 elements. And we also have has an action of mu3 in the 3 last elements, which correspond to a cyclic permutation of these three elements, which is set 3 set. So the numbers that I write down here, 1 and 2, correspond to this part of the action, and the rest is 1/3, 2/3, and also 1. So here I count 1 twice. So we have 1 and 1/2 for this part, and we have 1, 1/3, and 2/3 corresponding to this action.
Yeah, thank you. Thank you.
Okay. So this is the classical grading of Ito and rate by H of the set of conjugancy classes of a finite group of SLN. And now I want to relate this filtration by H.
I mean, the answer was Tom Sebastiani.
Yeah, at the end, this will be just the spectrum of the A5 singularity and the A4 singularity. So the point that I want to stress here is that, or to provide us a sort of explanation of why this spectrum can be computed in this manner. Okay. So the idea is that we can interpret the grading by H in terms of a certain.
Can I make a comment? Can I make a comment?
Yeah.
If you come back to the previous one.
Okay.
Here the whole point is that we are not at all talking about the spectrum yet. Not at all talking about the spectrum. This is just something that comes about the fact that this is a ghost loop space. And it's just about the representation theory of the groups. It has yet nothing really to do, just the Mackay correspondence, it's just how the discrepancy of the singularity behaves with respect to the H grading and the group representation. Correct, Enrique?
Yeah. So I will introduce a certain Hodge structure which is related with finite groups. And the point is that there is a sort of Mackay correspondence between this spectrum defined in terms of the Hodge structure associated to the group and the spectrum of the corresponding Duval singularity.
Exactly. So it's a new way to, it's a new, for Duval singularities, it's a new definition of the spectrum, just in terms of this algebraic Hodge structure that is a non-commutative Hodge structure, actually.
Yep. So
this is the point.
It's a sort of Mackay correspondence for the spectrum.
Exactly.
Okay, so let me explain very roughly how we can define or how we can relate the grading by H with or to put it in Hodge theoretic terms. And the point is, so let me start with a finite group G, and then we can consider the classifying stack of this group, which is purely ineffective orbital, which has just one point. And so from this geometric point of view, the category of vector bundles of this classifying stack is just equivalent to the category of finite dimensional representations of G, complex representation. So we have this correspondence between vector bundles over X and representations of G. Okay, so in this case, we have a projective generator for the category of representation, which is just a regular representation of the group, and this induces an equivalence between the representations of G and the category of modulus or of modulus over the endomorphism ring of the regular representation. So the endomorphism ring of the regular representation is just the convolution algebra of the group. And so we have an identification of the category of vector bundles over this classifying stack and the category of modules over this, convolution algebra. So in this way, or from the perspective of non-commutative geometry, this can be thought as we can rephrase this by saying that the convolution algebra of this group G is, in a certain sense, the algebra of functions over the classifying stack in G. Okay, so now we can use the technology from non-commutative geometry in order to define the Hodge cohomology and the periodic cohomology of this classifying stack in terms of the algebra, the convolution algebra of our group. So there is a way in which we can define Hodge complex of the convolution algebra in this way. So we have a certain chain complex associated with A and with its corresponding differential, and so we can introduce the Hodge cohomology of A. And moreover, in this, well, in general, there is a way to introduce another differential on the Hodge complex, which was introduced by Toms, which is related with the action of with a cyclic action of Hodge quotients in this way. So we have this new differential in this complex, and this new differential of Toms is compatible with with the compatible in this sense with the previous Hodge boundary operator, and this allows us to define, or we can define carefully in terms of this new cyclic differential of cones, the so-called periodic cohomology of the algebra. So the periodic cohomology of our stack X, the classifying stack of G, can be defined this way in terms of the convolution algebra of G. And in a certain sense, this periodic cohomology is, or can be thought as a sort of the rank cohomology of X in geometric terms. And moreover, here for this periodic cohomology, we have an action of we also have an action of the group of roots of unity, which is given just by this action by cyclic permutations of cochains, and this action is, well, in fact, we can think of this periodic cohomology as a sort of cohomology of the loop space of certain type of loop space associated with A, and so we have an induced action of mu on the periodic cohomology. So in the case of a finite group, or the convolutional algebra of a finite group, there is a theorem, or there is a computation of what is precisely the periodic cohomology. It's this result of Burgela. And for the case of a finite group, of the convolutional algebra of a finite group, the even part, so we have a grading of the periodic cohomology into even and odd part. We have just this grading of HP. We don't have the whole grading by integer, so we just have this even part and the corresponding odd part. And the even part, in this case, for a finite group with coefficients in the complex numbers, is given just by the set of class functions on G. So this is the set of functions, of complex valued functions on G, which are constant along conjugancy classes. So the dimension of this space coincides with the cardinality of the set gamma at the beginning of the top. Okay, so from a in fact, we can explain this isomorphism between the even part of the periodic cohomology and the set of. So this is basically the vector space spanned by the conjugancy classes, the set of conjugancy classes of G. And there is a more geometric way to look at this isomorphism in the following manner. So in fact, there is we can define in general for an arbitrary algebra A, we can define a Chern character, which goes from the K-theory of A to the periodic homology of A. And in fact, the periodic homology was invented by Combs in order to define properly this Chern character, or to have a receipt to take this for the values of the Chern character in non-commutative geometry. And once we pass to the complexification, so we have this Chern character from the K-theory onto the periodic homology, or the periodic homology of A. And the K-theory of A, in the case when A is a convolution algebra of a finite group, is just the representation ring of our group G. And when we pass to the complexification, then the Chern character becomes an isomorphism onto the even part. So we have the complexification of the K-theory of A, and we obtain an isomorphism with the even part of the periodic homology of A. So so we can think of this isomorphism here as a manifestation of this isomorphism when once we pass to the complexification, and this is just the pass from a representation into its character. So the characters, we can find the character of a representation of a finite group, and this is an element in the space of class functions, and this induces an isomorphism. So this Chern character is just this passing from the representations onto the character of of the representation. Okay, so also we can think of this Chern character and the isomorphism and this isomorphism here in terms of the so-called Seagal's totalization formula. So in general, so this is for a finite group, for the classifying stack of finite group, but we have a general version of this machinery working for arbitrary orbitals. So for arbitrary orbitals, the periodic cyclic cohomology correspond to the ordinary cohomology of the inertia stack of our orbital, which is a realization of the twisted sectors of the orbital, and there is an isomorphism between the orbital cohomology of X, which can be defined in terms of the K theory by complexifying the K theory, and the Chern character induces an isomorphism between the orbital cohomology of X and the ordinary cohomology of the inertia stack or the twisted sectors. Okay. So now that we have this periodic cohomology, the point is that we can introduce a Hodge filtration on the periodic cohomology. So there is a way to introduce a Hodge structure, a Hodge filtration, and in fact a Hodge structure on the periodic cohomology. We have we can put a Hodge structure on this periodic cohomology, and the point is that or the claim is that the Hodge structure induced on the periodic cohomology, which is just in our case is just the space of class functions of G, coincides with the H filtration, or it's related with the Hodge the filtration by H when G is a subgroup of SLN. So this correspondence between the filtration by H, the Hodge filtration on the periodic cohomology is allow us to relate at the end or to compute or establish a sort of Mackay correspondence between the decomposition given by the action of bioparameterizations of mu and the classical Stingray spectrum of the corresponding singularity, as I will explain a little bit at the end. Okay, so we have this Hodge filtration on the periodic cohomology, and this filtration is compatible with the action, with the cyclic action of mu on the periodic cohomology. And then we have here this claim that when G is a subgroup of SLN, then this corresponds exactly with the filtration of E2 and Ray. Okay. So now, in fact, we can. So we have this. We start with a finite group G, and then we can associate with this group G the classifying stack, and then we can take the periodic homology of this stack, and there is a Hodge structure here. Here we have a Hodge structure, which comes with an action of mu, and from this Hodge structure and the corresponding action of mu on the periodic homology, we can define, or we can introduce a certain kind of a spectrum, which I call here in this talk the stringy spectrum of the orbifold. So first, let me just say a few words about this map from the. So we have here the Grothendieck group of Hodge structures, which are. So this is we can think of the category of Hodge structures, and though with an action of mu. I will call this the monodromy so this is a sort of monodromy action, and so we have these monodromic Hodge structures, and we can construct the corresponding Grothendieck group of monodromic Hodge structures. And there is a map, and there is a well-defined map which takes which goes from the Grothendieck group of Hodge structures with an action of mu into the representation ring of this group of groups of unity. So this map is defined in terms of the filtration on the Hodge structure, and it can be so this mu is compatible with the filtration here, and this allows us to extract from a Hodge structure with an action of mu a certain virtual representation of mu. Okay, so however, the group this group mu is an abelian group, and the contrarian dual of this group is just the group Q mod Z. So we have every finite dimensional representation of mu can be decomposed as a sum of irreducible representations, but the irreducible representations of mu are indexed by Q mod Z. So if we have a representation, a finite dimensional vector space, complex vector space in with an action of mu, then we can decompose this V into a sum. So we have a decomposition like this into irreducibles. So let me draw this. Sorry. Well, let me write like this. So we have we can decompose this decomposition into pieces, which are indexed by the elements of Q mod Z, and this corresponds just so this action can be decomposed into its irreducible pieces, and each irreducible piece is related with a rotation by a certain angle. So just like in this case. So here we have the action of mu on this part, and this decomposed into its irreducible pieces, which are indexed by 1 and 1/2. And here we have a cyclic permutation action on this part, which decompose as a sum of 3 irreducible representations given by the rotation, the identity 1/3, an angle of 1/3 and 2/3. Okay, so we have this identification between. So in this way, we obtain an identification between the Grothendieck group of the representation ring of mu and the group algebra of Q mod Z. So we can have multiplicities for it in the decomposition into irreducible pieces for representation. So we can pass from this Grothendieck group into this one, which is just the group algebra, and then we can think of this of the corresponding element of the group algebra as a certain kind of a spectrum. So if we start with an orbifold, or with this orbifold BG, then we can take the periodic homology of X, and this is equipped with a monodromy action of mu, and then we can use this map in order to decompose the corresponding representation of mu into its irreducible pieces, and the elements which appear in the decomposition of the corresponding representation of mu can be defined as the spectrum of the orbifold. So we define in this way the stringy spectrum of an orbifold, which is which in the case of a finite group G is defined completely in terms of the representation theory of G. So, for example, for instance, when we have a finite group of SL to C, then we can construct the corresponding quotient variety, which is a singular surface in this case. And for this, so we have this Kleinian classification of finite subgroup of SL2, and we have the corresponding surface, singular surfaces. And there is a classification of these singular surfaces. We can write down these quotient singular varieties in terms of, or can be realized as hypersurface singularities. So there is a well-known correspondence between these the groups in these Kleinian groups and the corresponding singularities, which are hypersurface singularities, called the Val singularities. So we have this correspondence between certain kind of hypersurface singularities, the Val singularities, and the Kleinian subgroups of SL2. So this is the context in which the classical Mackay correspondence appears, and in this case we can compute, or we can so we have a finite subgroup of SL2. We construct the singular surface associated to this group, and then we can relate this with a hypersurface singularity R. And for hypersurface singularities, there is a notion of the spectrum that is Steenberg, so we can compute the Steenberg spectrum of the corresponding hypersurface singularities, which are in this way. And the point is that, or the question could be, how is related the spectrum? So we can define the Steenberg spectrum of the hypersurface singularities, and we can also define the stringy spectrum of the associated Kleinian groups of SL2C. And the question is, what is the relation, if any, of these between these two spectrums? And so the answer is that, in fact, we can prove a certain kind of Mackay correspondence between the stringy spectrum given by which is given in terms of the group, and the Steenberg spectrum, which is given in terms of the hypersurface singularities corresponding to this finite group. However, in order to prove, in order to prove this Mackay correspondence, we need, the approach that we take is to use the techniques of motivic integration and the associated motivic zeta functions. And so, by means of this technology, we can prove this Mackay correspondence, and in fact, we can compute the Steenberg spectrum of the Val singularities in terms of the representation theory, purely algebraically, of these groups on the left. Okay, so I think that this is all that I want to say. Thank you.
So, do you think
Any questions?
Yeah. Sorry. Do you think this can be extended beyond the singular?
Yeah, in fact, the stringy spectrum can be defined for an arbitrary minimum for a step, and so yeah, there's so this seems to work for Val singularities, but in general we can have an arbitrary hypersurface singularity, an isolated singularity, and so we can have something like this, a variety together with a singular subvariety, which can be given as the fiber of a certain map. And in terms of this pair, which is the singular fiber and the ambient variety, we can associate to this pair. To this pair, we can associate an orbifold by. So we can take the singularization of the fiber and embed it. Resolution of singularities, but within the category of the minimum for stacks. So to this pair, we can associate a certain orbifold, and then we can pass to the stringy spectrum of the orbifold, and the Steenberg spectrum of the original isolated singularity will be related by a certain correspondence between these two things.
In a certain sense, Ludmil, this is a theorem that says that the resolution of singularities transform a non-commutative spectrum into a commutative spectrum. This is more or less what this is saying. This generalized Mackay correspondence.
And in fact, it shows something which is known in this case, that if the spectrum puts canonical resolution or the splitting more is not dependent on the chosen.
Any other questions?
So I have one question.
No, I
Hello. Yeah.
Yes.
Yeah, could you explain this motivic? I mean, how a little more about this the spectrum, how you obtain spectrum via this motivic integration technique?
Yes, so the spectrum of the orbifold can be defined without any use of motivic integration. So we can take the periodic homology of the orbifold and the associated Hodge structure and its action by loops, and then we can define in terms of this. Just in terms of the periodic homology, we can define the string spectrum of the orbifold. But we need to use motivic integration and zeta functions in order to show that that the correspondence between or the way to look at the spectrum in terms of the orbifold is related with with other resolutions of singularities. So the invariance, in some sense, we need to use motivic integration in order to show the invariance of this string spectrum.
I mean, but did you, I mean, need to, so anyway, how can relate to this non-commutative invariant to this commutative spectrum? So, and it seems that you use the technical motivic integration to do that. Am I right?
I think that we need motivic integration just to prove the invariance of the string spectrum. So the invariance of the spectrum, the spectrum can be defined intrinsically in terms of the orbifold, in terms of the orbifold by means of the periodic homology, but the invariance when we pass to other other ways to resolve the singularities in order to prove that there is no change in the string spectrum and or the spectrum associated with the resolution of singularities is so in other words we need to use motivic integration to prove the Mackay correspondence of the string spectrum.
This is not to say, though, that we don't use motivic rings before motivic integration. Motivic rings are used, K0 groups are all throughout. But for the Mackay correspondence, we need the additional ingredient of motivic integration.
Additional, could you say one more time, additional ring?
No. I said for the Mackay correspondence, we need the additional ingredient of motivic integration.
I see.
But K0 groups are used throughout.
Okay, I see. Okay, thank you very much. Thank you.
All right.
Let's thank the speaker again. Let's thank the speaker again for a very nice talk.